Hey everyone, and welcome to The Explainer. We often think about getting energy out of the ground as a straightforward process, but sometimes it's anything but. Today, we're diving into a really clever solution to a tough problem. What on earth do you do when the oil you're trying to get is just too thick and stubborn to pump?
Right, so I want you to picture this. There's a huge oil reserve, miles beneath our feet. We know it's there, but the oil itself is so thick, so goopy. It's like trying to drink a super thick milkshake through a tiny coffee straw. It just won't budge. So what's the game plan when the standard methods completely fail? And this isn't just some thought experiment. It's a very real challenge with what's called heavy oil. We're talking about stuff with such a high viscosity that your typical pumping methods are basically useless. And this is a huge deal. There are potentially trillions of barrels of this stuff locked away, just waiting for a smart way to get it out. Now, it's not always just about the thickness of the oil. Sometimes the rock formation itself is just too delicate, or the depth makes it crazy expensive to use the usual brute force high-pressure techniques. You can't just throw more power at the problem. You've got to find a more elegant, smarter way in.
And that's where CO2 injection enters the picture. But here's the thing, even when you decide to use CO2, there are two totally different ways to do it. You can either try to get the CO2 to mix with the oil and thin it out, or you can use it to physically push the oil out of the way.
So let's break down those two game plans. On one side, you have miscible flooding. Think of the CO2 as a solvent. The goal is to get it to completely dissolve into the oil, making it thinner and easier to move. Then you've got immiscible flooding. Here, the CO2 and oil stay separate, kind of like oil and water. The CO2 acts more like a big piston, a bubble of gas that physically shoves the oil forward.
So what decides if the CO2 is going to mix or push? Well, it all boils down to one single critical factor, pressure. To get that CO2 to actually dissolve into the oil, you have to hit a very specific, and usually very high, pressure level inside the reservoir.
And that magic number is called the Minimum Miscibility Pressure, or MMP for short. The analogy of sugar dissolving in water is perfect. You need the right conditions, right? Well, for CO2 to dissolve in oil, you need to reach that minimum pressure. If you can't hit that MMP, it just won't mix. It's going to stay separate no matter what. So if you can't mix, you've got to push. Let's zoom way in and see how this squeezing actually works at a microscopic level deep inside the tiny pores of the rock. Okay, so think of it as a squeeze play. First, the CO2 you inject goes into the rock's tiny little pores as separate bubbles. Then, these little bubbles start to link up, kind of merging into bigger pockets of gas. As these gas pockets grow, they create pressure and physically squeeze the trapped oil out of all those nooks and crannies, pushing it forward toward the production wells where it can finally be pumped out.
So the most important thing to get here is that with this immiscible method, you're not really changing the oil itself. You're not trying to alter its chemistry. All you're doing is using the expanding CO2 gas to maintain pressure and provide the raw physical energy needed to shove that stubborn oil out of the rock.
And this is so cool because this brings us right back to that original problem. This whole pushing method, it turns out to be the absolute perfect hero for that super difficult challenge, those heavy oil reservoirs. And why is that? It's because that super thick, stubborn, heavy oil has an MMP, that minimum miscibility pressure, that is just astronomically high. I mean, trying to generate enough pressure down there to dissolve CO2 into it would be pretty much impossible. It's just not going to happen, technically or economically. And don't just take my word for it. This is why experts over at Bowsher Energy say that for these kinds of really challenging reservoirs, immiscible flooding is a truly viable option. It's not a sloppy second choice. For some situations, it's the only choice that makes sense. It creates a path forward where one just didn't exist before. But you know what? The story doesn't even end there. It turns out that choosing to push instead of mix, when the conditions are right of course, comes with a whole bunch of other operational benefits that can make a project safer, cheaper, and just all around smarter. Because you're not trying to hit that ridiculously high pressure target, you can operate at much lower injection pressures. That right there means you save a ton of money on gas compression costs. It also means you're less likely to damage the rock formation itself, and you even lower the risk of things like induced seismicity. You add it all up, and the project's bottom line just looks a whole lot better. And really, this chart kind of says it all, doesn't it? When you put them side by side for the right type of job, the high-pressure methods come with high costs and high risks. The immiscible approach, on the other hand, means a huge drop in both. It's just a more efficient way to go.
So in the end, it's not like one of these methods is just better than the other one. It's a classic engineering story. You have to pick the right tool for the right job. Whether you mix or you push depends entirely on the unique personality of the oil and the rock that it's trapped inside.
And that kind of leaves us with a really big question for the future, doesn't it? As all the easy-to-get energy sources become harder to find, will these really clever, highly specialized solutions like immiscible flooding stop being a niche tactic and start becoming the new standard for how we power our world? Something to think about.